Yeah, it's not like they are attacking you. Yeah, exactly. No. Punching. Maybe. Well. Oh.
Okay. Good morning, everyone. I think it's time to start. So we're going to continue with the neural networks. Oh, by the way, again, another reminder just to suggest you to start doing SVM right now, because it will take some time to go through the slides, and from the discussions with students in office hour, is that, well, it's not hard, but you need to know quite a few notations and take some time to digest how to reason on that. So please start to do it right now. The implementation is pretty straightforward, but you do need why you can implement in that way. Also, you need some time to look at the documentation of SciPy optimization, for example, to know how to call those optimization packages. We don't want you to implement quadratic optimization from scratch. Okay. Okay. The schedule is about neural network is as follows. So today we're going to continue talking about neural network. We're going to talk about how to make prediction. Suppose your neural network is given, including the parameter values. Right? This is called forward pass. And then we'll talk about the general training framework for neural network. And then we're going to touch the key component, which is called backpropagation. So you see that the backpropagation can address the computational bottleneck in the calculating the gradient of the loss with respect to neural network. Otherwise, it will be very hard and inefficient. And then on next Tuesday, our another TM, Shibo Li, he will give a tutorial on the modern neural network libraries. Maybe you have heard of that. How many of you have heard PyTorch and TensorFlow? Oh, nice. That's great. So that means these two libraries are really well known now. So although our class is kind of like a fundamental class and an entry-level class, that's why we request every student to understand the whole principle, the ideas, and how to train that. That's why in our homework, you are requested to implement backpropagation by yourself and test them on real data to show that your implementation makes the learning of the makes the neural network learn properly. But in practice, including your course project, right, or any other your research projects, or your job, which involves some like deep learning steps, we always encourage you not to reinvent wheels. Right? Try to leverage the most advanced tool to facilitate your usage of neural network, so that you can focus on your main energy on developing new models, test on new cases, develop new applications, and so on. So that's why we would like to have our TM to first give a tutorial on using PyTorch. Hopefully that will benefit your course project if you want to use some neural network to conduct a Kaggle computation or do your own research project. But in your homework, please don't use PyTorch. Implement by yourself. Oh, by the way, there might be some benefit question. Encourage you to implement PyTorch version for your neural network algorithm. But the obligatory problem will be you have to implement backpropagation by yourself. Okay? And then the following Thursday, we're going to finish up all the details about backpropagation because it's so important. I'm going to give a very concrete example. I will give a 3-layer neural network. We're going to do this calculation step by step by hand, and so that everybody is expected to know the whole computation tricks by following that specific example. Okay? Any questions so far? Oh, wait. Oh, another thing is about the course project report, the final report. We actually have released the deadline. I think it should be the end of the week we did the final exam. Our final exam will be December 15th. Students, this classroom from 8 a.m. to 10 a.m. I know this time is not very friendly, but this is scheduled by the school. I don't have the authority to change that. But then we're gonna have like 3 more days for you to finish up your course project report. Don't write too long, just write enough information. That'll be fine. But here, just to give you a reminder, if you haven't made any progress after the midterm report, please start doing it right now. Okay? Because you do need some time to wrap up the results and write some summary analysis in your report. Okay, it's not very feasible to finish all this like in 1 day or 2. Okay, so let us continue with the neural network. So in the last lecture, sorry, is this too long? Okay, so in the last lecture we give a formal definition of neural network. Right? So the standard neural network is defined as a directed acyclic graph where each node in a network represents a neuron. Right? And someone asked, why not I can't add a cycle? Well, I say yes, you are allowed in the frontier research. Right now, many researchers in this area, they're trying to invent some like weird architectures to address some specific problems. Because we're talking about the conventional neural network, that's just stick to the conventional definition. So directly acyclic graph meaning that there's no cycle, and each node represents a neuron and are connected from the neurons in the previous layer. So we can as the layer network, right? So the bottom layer is the input layer. So the input neurons are just the features from the data, the input features from data, and then those neurons in the input layer are connected to each neuron in the next layer. And then each neuron in the next layer, which is now referred to as hidden layer, are then connected to the layer above. Suppose we only have like 2 more layers, so then the final layer will be this one, right? So and along with this network are the parameters, right? So the neural network are determined by the weights associated with each edge on this network, right? So and it follows a very simple rule to compute the value of each neuron, right? The rule is as follows. Right? So to compute each neuron, right, we just multiply each incoming neuron which connects to this neuron by the weight on the edge connecting them. And then we add them together. This is the first step. It's called linear combination or dot product, whatever you like. And then we apply an activation function. So the activation function can be a lot, right? It can be linear unit, meaning that, okay, it just returns the input itself. Or thresholding, this is used in a linear threshold unit, right? And sigmoid, much more common. And rectifier linear page. So the neuron, the value of neuron, which is referred to as output here, is computed by the two steps. Right? First, do a linear combination of the input neuron values and then perform an activation function. Right? And now, then you collect the values of each neuron, and then those neuron values are sent to the neurons in next layer and follow the same way to calculate the neuron values. So the definition of the neural network is pretty simple. Right? It just uses very basic components like linear threshold units, sigmoid units, etc. Right? You just stack them together and concatenate them together layer by layer. And the computation just follows two rules. Linear combination, nonlinear activation. Linear combination, nonlinear activation. But the power or the capacity of such a model is very surprising. We have mentioned that to use a simple neural network based on threshold activation function to show how expressive it is. Right? So now I want to ask any question regarding the definition of neural network. Okay. Oh, one thing I want to emphasize. So, although in many neural networks, the substructure looks kind of like symmetric. Like you can see that this neuron are connected by all the neurons in the previous layer, and this neuron is also connected by all the previous neurons. What's the difference? The difference is reflected on the weights on the edges connecting this neuron and this neuron. They are really different. And the learning procedure usually gives you total different values of those weights. That means, okay, they might share kind of local structures, but the values computed are usually vastly different. Okay? So now, let us talk about how to make prediction. How to make prediction with neural network is called forward pass. Right? So as we mentioned before, we're gonna first talk about the definition of neural network, and then we're gonna talk about how to make prediction with neural network. That means we assume the neural network architecture is given, and we know the appropriate values of the weights. Then suppose you're given a new example, the input, right? How can we calculate the output? This whole procedure is called forward pass. Why? Because you can view the input layer is here, right? And output layer is there. So we view the direction that from input to output as the forward direction. And then the calculation procedure is kind of layer by layer. Starting from input layer, and next layer, next layer, until you reach the output layer. Okay? So we're going to use this simple two-layer neural network as our running example to showcase how the calculation is carried out, right? So, by the way, we call it two-layer neural network is because we didn't count the input layer. So, if you really count how many layers in total, adding the input, that should be 3. But usually we call a two-layer neural network. So, don't be surprised. So, as we know, on each edge there is associated with a weight, right? So to avoid being confused by different weights, right, we're gonna introduce some naming condition or naming convention on that. This is another kind of notation. It's kind of perhaps it's a little bit annoying, but it's really important because we need to know which particular weight we are operating on. Right? So please bear with us, bear with me. So first, we're going to use this vector x to represent the impact. So you can view it as the vector which consists of all the values or neurons in the input layer. Right? And then we use this vector z to represent the collection of the hidden neurons in the hidden layer, so including z0, z1, and z2. Okay. And finally, we use y to denote the final output neuron of our neural network. And to be consistent with the linear threshold units, right, we introduce this kind of like a graphical representation of linear classifiers, but also can be viewed as some basic component of neural network. Right? We also introduce some constant features, which is called bias features. Why we call it bias features? Because the weight on the edge which connects those constant features can be viewed as the bias term, right? So we set these two gray nodes or neurons as our bias feature, and they are constant. They're simply 1. Right? To say why the bias term comes from, right? So let us take a look at Z1. So following the rule we just mentioned to compute the value of Z1, we're going to multiply the value of each input neuron by the weight on the edge, right? So this weight times x1, right? And this weight, the weight on this edge times x2, plus the weight on this edge multiplying x0. And x0 is 1. So you can see that this linear combination has the same form of the linear classifier, right? So it's you can view it as w1 x1, w2 x1 plus some w0 times 1, right? Because x0 is 1. W0 is actually the bias parameter. Does it make sense? Any question regarding these notes? Yeah, similarly, if you calculate Z2, you'll see that there are another set of weights combined x1, x2, and x0. Again, because x0 is 1, so the weight on this edge between x0 and Z2 is the bias parameter for Z2. Right? So this is just our convention. You can, in practice, you can choose to not adding any bias features. It's up to you. But in most neural network literature, they tend to add those bias features to be consistent with our linear threshold units. They appear first in the whole development history of the neural network. Okay? And another important convention is that the calculation of all the neurons we discussed before is going to apply some activation function, right? After the linear combination of the input neurons. And now apply some activation function. You can choose sigmoid, you can use tanh or sine function. But in the output layer, the rule of thumb is that we're going to only apply linear combination. We do not apply any nonlinear activation function. So that is when we calculate y, we just do this weight multiplying with z0 plus this weight on the edge multiplying z1 plus this weight multiplying with z2. Don't get y. We no longer apply any sigmoid transformation or sine function, whatever. What's the reason? No reason. It's just the convention. So usually in the last layer, or in the output layer, people just do a linear combination of the neurons in the second last layers. That's it. Well, in practice, you can also choose to apply your final additional activation function. It's really up to you. But here we just stick to the tradition. But this does not mean, this tradition is weird, because this can be viewed as, you can imagine, because your final prediction y is a simple linear combination of z0, z1, z2, right? So if you view z1, z2 as kind of matched feature from the original input space, you can view it as consistent, as we discussed before, right? Previously, when we talked about how we extend linear classifiers to nonlinear classifiers, we said that we can apply some nonlinear feature matching. Right? We map the previous features into a set of new features. Then, in the new feature space, we'll apply some linear model. Right? So, if you use the traditional definition neural network, actually, you can view a neural network as a specific, special feature transformation, right? Or feature mapping. And in the last layer, right, you just combine the mapped or transformed features to do a classification, to do a linear model. So the consistency is good. Any questions so far?
The weights are depends on neurons or layers. For example, the weights between x1 and z1 and x1 and z2 are same or
are different. The weights are dependent on the edge. It's not dependent on specific weights. Well, partly depends on, but is uniquely determined by the edge, namely both the starting node and the ending node, which is going to reflect in our notation in a minute. Any other question? Okay. Yeah, the final output, we're going to apply linear activation function. This is just the same. We do not apply any nonlinear transformation, just use the original value, right? Okay. So now, to index different weights, we're going to use a little bit tedious notation. Right? So, for each weight to differentiate from other weights, we're going to use both superscript and subscripts. The superscript indicates the index of the target layer, so namely which layer this edge points to. Right? For example, this edge points to the alpha layer, so the target layer index will be like O or whatever, right? And this edge points to the hidden layer, so the target layer in the superscript is H, whatever, or some integers if you want, use them to index layers. That's totally fine, right? And then in the subscript, we're going to use two indices. The first index is the node where the edge starts from. Like on this edge, right? It starts from the first node in the hidden layer, so the from index is simply 0. Okay? And the next superscript, next subscript is the index of any node this edge points to. Again, here we can see, look at this edge, right? So if we index the output node with 1, right, and then we should put 1 here. So that's the way we denote each different weight, right? So the reason we use this is because the weights are really dependent on edges. It's not determined by others, right? To uniquely retrieval each weight, you're gonna give sufficient information. Let us look at this weight, right? So this weight denoted by W010 indicates is from neuron 0. It is on the edge, connects to the alpha layer, right? Which is shown here. Right? Target layer is alpha layer O, right? And then it starts from neuron 0 in the second last layer, and then neuron 1 in alpha layer, because there's only one neuron in the alpha layer, so its index is simply 1. Right? And similarly, we can take a look at here. Right? So this weight is denoted by W22H. Okay. First, the superscript H indicates the target layer is hidden layer, meaning that the only node of this edge is in the hidden layer. Okay? And the starting node in the edge, of course, is in the input layer. Right? So the index of the input layer, which is the from node, is 2, meaning that x2. And the ending node in the hidden layer is indexed by 2, meaning z2. So this indicates, okay, it is on the edge, pointing from x2 to z2. Does it make any sense? Does it make sense? Any questions so far?
Just to be clear, if you had multiple hidden layers, you have a different notation for each hidden layer with H, right?
Yeah, exactly. Yeah, like if I have like 10 layers, of course, I'm gonna use other indexes to denote different layers. Like for example, I can index the input layer by layer 0, and the first hidden layer by layer 1, second hidden layer by layer 2 until the end layer. Any other question? This is important because later we're going to see a lot of examples showing how to calculate the derivative and with respect to different weights. I don't want anyone to be confused at that time. So I want everyone to be on the same page. Okay, for another tedious example, this one, right? So the W01H indicates this is the weight on the edge which connects to the hidden layer, right? H here. And the starting node is on the one layer before the hidden layer, node 0, which is x0, right? The ending node is the node 1 in the hidden layer, which is v1. Okay. And again, let me emphasize again, although in theory all those weights can take the same value, in practice they are usually very, very different. Even be kind of like symmetric in local structures. Okay? So now, let us look at how to predict with a neural network through this forward pass procedure. Suppose we're given an input x, right? So meaning that I know the value of x1 and x2 in our example, right? Of course, x0 is 1, right? So we're going to gradually or sequentially compute each neurons in the next layer, right? That includes Z1 and Z2, right? So how to compute Z1? As we mentioned before, we just do a linear combination of all the neurons in the previous layer connecting Z1, right? So we're going to multiply X0 by W01H, right? The weight on the edge connecting X0 and Z1. And of course, X0 is the bias feature, it's simply 1, so you got W01H, right? And then plus X1 multiplying the weight on the edge connecting X1 and Z1, right? So this weight is denoted by W11H, right? Starting node 1, ending node 1, and target layer H, right? W11H times X1, and then plus X2 multiplying the weight on the edge connecting to Z1, right? The weight on this edge is denoted by W21H, right? Starting node 2, ending node 1, hidden layer is the target layer, right? So you finish the first step. You just do a linear combination of the input neurons weighted by the weights on the edges connecting to Z1, right? And then you need to apply activation function. So we use this sigma to indicate a general any activation function you want. Right? It can be sigma, it can be tan H, it can be rho, whatever. Right? So we calculate the value of neuron Z1. We follow the same procedure to calculate the neuron Z2. Okay. So again, you're going to do a linear combination of the input neurons in the previous layer, right? But now they are weighted by different set of weights. Why? Because Z2 are connected from different edges, right? So you do a linear combination, and be careful, there's the notation is different. And then you apply a nonlinear activation function, right? So in this way, you have finished the computation of the neurons in the next layer, right? You got the input layer here, they are known, and they are given, and then following these rules, you calculate the values of all the neurons in the next layer. Remember Z0 as well, right? And then we move to the next layer, which is the outer layer. And in the outer layer, remember, we follow the convention. We only do a linear combination of the neurons in the hidden layer, right? So there's no actual activation function, right? So you just multiply W0O, which indicates the attribute here, times Z0. Z0 is concentration 1, right? Plus Z1 multiplying with the weight W110, right? Starting node 1, ending node 1, and target layer, alpha layer, and plus W21O times Z2. So once you get the value of the alpha neuron, you finish the prediction. This is called forecast. Right? And of course, if you have multiple layers, right, not only one hidden layers, you have actual layers here, 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 and here, 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 right? You just follow the same procedure as computing Z1 and Z2. And layer by layer until you reach the alpha layer and do a linear combination of the neurons in the second last layer. Any questions so far?
An example of linear combinations for output.
Linear combination for what?
Output.
For the output? Usually it's not necessary to perform some linear combination output. But it depends on how you define a loss. So later we'll talk about the training procedure. Well, you might have multiple outputs. Maybe you should combine the outputs to fit some data. Yeah, there might be a linear combination, but usually this is your final prediction. Like you want to predict the temperature today, right? When you calculate the output, it gives you a continuous value. We can use that as my prediction for today's temperature.
I mean, the linear combination that you put for the output, the W01 layer 2, like that.
W01 layer 1.
You put a function on out on output here, and the neuron of Y.
You mean the output is viewed as function of those weights? Yeah, exactly. The output is essentially a function not only on W01, all of this, but also on this. Right? Because the computation of output depends on all of those weights on edges, right? The special thing, the special thing is that, okay, the computation procedure of Y is layer by layer, but it really depends on this. Okay. But that's a good insight, because later we're going to talk about the idea of a training neural network. Right?
I think you mentioned it, but can you redefine what segment is? Is that the nonlinear transformation?
Yeah, it's any transformation function or activation function. It can be sigmoid activation function. It can be sine function. It can be sine function or cosine function. This is just a general notation telling you that there is an activation function, but there are a lot of choices. Other questions? Okay, great. So the forecast is relatively straightforward. We just follow the rule, right? We follow the order to compute the neurons layer by layer until you reach the output layer. You finish the prediction, right? And now we're going to talk about the key component of our neural network, how to conduct the training, right? And of course, the key technique in the training is called backpropagation, which is our concentration. Right? So let us first give some kind of formal description about the neural network training procedure. So we assume that the neural network architecture is given, meaning that we know how we lay out those neurons, like how many layers do you want to use, and each layer how many neurons will be placed, and also among those neurons, how they are connected across the layers. They are all defined, predefined. And also we have already determined the type of activation function. Right? Maybe someone prefers sigmoid, someone prefers 10H, right? Someone prefers ReLU. Right? So all this model have already clearly specified. Right? And then we have collected a data set of label examples. So the data set is essentially pairs of the input vector xi and output label yi. Y can be binary or can be continuous, whatever. It depends on the task. Then the goal is to learn the weights of the neural network from data. Right? So remember, the weights are essentially on edges. Right? So we just want to identify those edge weights on the neural network. Once we call this procedure as training procedure. Once we get those edge weights, we can then perform any types of prediction we want, right? By following the forward path we just discussed. So this is the formulation. And how do we learn the weights of the neural network? Okay. The insight is here, as some of you have just mentioned. Although this whole procedure looks like step by step, if you just look at the neural network output, right, you can view it as a function parameterized by its weights. Right? So in other words, you can write your output neuron, prediction of the neural network, right? As a particular mapping, a particular function, which is determined by all the weights on the edges, right? Of course, it's also determined by x, which are input neurons. And different weights, the choices of different weight values will obviously cause different final output neuron values, namely the prediction. Right? Then our goal is to find the optimal values of weights for this neural network. This is called training procedure. Right? So now you can see from this notation, neural network is nothing different than the linear regression. Right? Remember, for linear regression, we just replace this neural network mapping by some linear function. Linear function of x, that is W transpose x plus product B. Right? But now, my predictor is much more complex. Right? If you want to compute the prediction, you're going to do some layer-wise linear combination, activation, linear combination, activation until reach the output. Right? But the output, after all, is still a function of the input and also the parameters. Now I want to ask your suggestion. What kind of strategy do you think will be good to estimate the weights?
Some sort of gradient approach.
Yeah, gradient approach. A gradient approach is based on what?
The gradient, the derivative.
Yeah, the gradient derivative. But the gradient derivative depends on what? you need something to calculate gradient, right?
Loss function?
Yeah, exactly, right? So remember, when we train a linear regression model from data, how can we do that? Because our predictor or our output is some linear function of the input and some model parameters. Right? To estimate these model parameters, we want to come out with some loss function. Right? Measures how well your model fits the data, right? And then we convert the training into an optimization problem. Right? We minimize the loss function with, for example, gradient descent to find the optimal parameters. Now we follow the same framework or same strategy to train a neural network. Right? We can also come out a loss function, right? For each training example xi, we can use our neural network to make a prediction, and then compare the difference between the ground truth label yi, right? Which is described or measured by a loss function. Then we just sum over the loss, sum over the loss of all the training examples. This is our training objective, right? And then we just minimize this objective function. And of course, maybe only fitting the training data well is not sufficient, right? So we can choose to add one more regularizer. Right? This is similar as what we have done for support vector machines, right? We want to add the square of the weights, right? And in support vector machines, that means you're going to maximize the margin, right? And we can design whatever regularizer we want, right? And for perception, at least mean square regression, we only fit the training data, not adding any loss. So, but overall, the framework is the same for linear models, for non-linear models. Right? We still come out some kind of loss, and then we write down our objective function, and then we just calculate the gradient of the objective function, update the neural network weights until convergence or some kind of other stopping criteria are met. Right? Any questions so far? Is everyone good with this training strategy? Okay, so now I want to ask, what kind of loss do you think is there's no answer. I mean, there's no unique answer that come up. You can suggest whatever you want. Any thought? Any idea?
Mean squared error.
Yeah. Yeah. Excellent. Okay. Mean square error. The same thing as linear regression. Right? It's easy to calculate the derivative and it's easy to deal with. Okay? Of course, you can come up with other laws, but just we can just use one simple and commonly used choice, right? Square error. So if we go back to our running example, right? So we follow given the current parameters, right? The weights on those edges. Right? We want to calculate loss. We're going to first use the forward pass, starting from the bottom layer to calculate our prediction, right? When we get our output y, suppose the true level for this example is y star, then we can write the square loss for this example in this way. Is half y subtracted by y star, the difference between the prediction and ground truth and x squared. Right? But remember here y, the output of the neural network, is a highly nonlinear function. It's not a linear function at all. Of both the input x and also the edge weights. And then we can add up the square loss over all the training examples. And perhaps with an additional analyzer, and then our objective is to solve this minimization problem. So now I want to ask what kind of frameworks shall we use to optimize this loss function? Yeah, gradient descent. And what else? Yeah, stochastic gradient descent, right? Remember, we actually have discussed in the last lecture, neural network is powerful in that it is highly expressive, right? It's highly flexible. The larger the network you have, the more expressive it is. The more complicated functions it can estimate or approximate, right? So that's why neural network is really powerful when you use big training data. Right? If you just have 50 examples, it's not very wise to apply neural network because it is always easy to overfit. Right? But for the large training data, like you have millions of training examples or even billions of training examples, which kind of optimization algorithm is our favorite? The stochastic gradient descent, right? So we have discussed the difference between the advantages and disadvantages of gradient descent and stochastic gradient descent, right? When you have a large data, it's really unwise to apply gradient descent because to calculate the exact gradient, you have to go through the entire training set, right? If you have to go through like 1 million training examples to calculate one gradient, then update once. Right? But if you use stochastic gradient descent, whenever you have seen a new example, you can calculate the stochastic gradient and then update the model immediately. Right? So the efficiency is much higher. Right? So for neural network, the most use cases will be based on stochastic gradient descent. So this is our loss function over the training set. Right? It's a loss over every training example I measures the difference between your neural network prediction and yi, right? So we're going to apply the same algorithm framework as we did before. Right? So if your program, if your code is written very clearly, I will suggest you to reuse your previous code. Right? Just plug in the backpropagation component, that will be fine. So we're going to first initialize our neural network parameters. But here I just want to emphasize, in practice, neural network parameters are usually not initialized as 0. We won't initialize as 0, and often it's often the case that if you use 0 initialization for neural network, the result will be very bad and very bizarre. And instead, we're going to use random initialization. You can use some Gaussian standard anomaly distribution to generate samples, and those them as our neural network weights initialization. Okay, and then we're going to go through the data set for big T epochs. Okay? And of course, you need to manually tune the number of epochs. Inside each epoch, we're going to randomly shuffle the training set, and then sequentially process each training example. For each training example, xi, yi, we treat this example as the entire data set and then compute the gradient of the loss. Right? We just compute the gradient of the loss with respect to the model parameters on this particular example. Then this gradient is called the stochastic gradient. Then we'll update the model parameters by subtracting this stochastic gradient multiplying some learning rate gamma t. Right? So as we discussed before, if you want theoretical convergence guarantees, you have to make a appropriate schedule of gamma t, right? And you can use the same schedule we suggested for you to implement SVM. That should be enough. And one thing we should be aware is that because the prediction of neural network is a highly nonlinear and a non-convex function of the parameter value. So it's not the same as SVM or other linear classifiers. The whole loss function is non-convex function. So that means it might have many different local minimums. That's why the initialization matters. Like, you can imagine the surface of this function is kind of wavy like that, right? So you have a different values and stationary point. Right? Of course, if you starting from here, you might converge at the first value. While you starting from here, you might converge at the 5th value. Right? So it's so the initialization can take a very important impact on the final result. That's why there are a lot of tricks to do the initialization for neural network. And if you take a look at the PyTorch library or TensorFlow library, they have provided I believe about 10 different ways to do the initialization. Random initialization. Some uses truncated normal distribution to generate random samples as the initialization. Some uses other distributions, and a lot of them. And the different types of initializations are reported to work well for different applications. So in your practice, choose using an appropriate initialization is also important. Like in image classification, there's a very famous initialization invented by some Facebook researcher, and people just use his name as the initialization. It's called HE initialization. Chinese pronunciation is He initialization. It's very famous. If you're doing image classification and using ImageNet or ResNet, those kind of architectures, that one is the first choice. Okay. So it looks like we have addressed everything, right? So we just reuse the previous framework we're quite familiar with, right? And just to follow the standard procedure, we can train a neural network. Have we addressed everything? Right. What's the remaining problem? Yeah. Actually, this is a key problem, right? We have never talked about how to calculate the gradient of this loss. Only you can efficiently calculate, you can conduct this. Otherwise, you have this framework. This framework won't work. So it was easy for small back machines, at least means square regression, to calculate such gradient. Right? We have done that manually before. It's pretty straightforward. It only has one layer. Right? But for neural network, it is much more challenging. Why? Because the neural network is really very large. You have many layers. You have many parameters. It's very common to have like hundreds of thousands of parameters. Like you have 2 layers. Each layer has 100 neurons. It's very small network, but even it's 2 layer, 100. Those 100 neurons per layer will contain like 10,000 parameters. Right? But this is just a tiny network. And the recent research, like in image classification test, they use 250 layers network. Right? So you can imagine how many parameters it is. Right? So if you just calculate the gradient naively, it will be very, very inefficient. Even if you use the classical descent framework, because your bottleneck is in computing the gradient for each weight element, and such weight elements are millions of, or tens of millions of. It's pretty common, right? So you have to address that bottleneck right, before your implementation. Otherwise, it won't be practically useful. So, and the backpropagation is the efficient implementation of the gradient calculation. So, it is essentially a very smart application of the chain rule. So everyone is familiar with chain rule, right? So everyone have used them and practiced them during your calculus course. So I believe this is not unfamiliar with. This is not unfamiliar, right? And backpropagation actually combines the neural network architectures and the chain rule to avoid repeated computation and to catch the intermediate results, so that you can use one path from output layer to the input layer to calculate the gradient with respect to each weight. That's why it's called backpropagation. When we do the forward paths, when we do the prediction, we calculate the order to calculate neurons are from the input layer to the output layer, so it's called forward paths. And now, when you calculate gradient, the order is from the output layer to the input layer. That is why it's called backpropagation. Okay, so before we proceed to backpropagation, I just want to check what we have discussed so far. Right? So right now, we know that if we have a neural network, we have identified structure, the type of activation function, weights, we can make prediction for input. This procedure is called forward pass, right? And then to perform training, we're gonna collect a set of training examples. We have the true label of each input, then we can define the loss for that example. And then, right now, our goal is to compute the derivative of the loss with respect to each of the neural network weights. Once we get this derivative, we can take a gradient step in the SGD framework. Okay, this is our current setting. Any questions so far? Okay, so to talk about the detail of backpropagation, let us first review the definition of chain rule. And also, I want to associate the application of the chain rule to some graph representation of the dependency between the variables. Okay? I know everyone is familiar with that, but let us just refresh our mind. Right? So chain rule, briefly speaking, is a way to compute the derivative for composite functions. Right? So if z is a function of y, right? But y is a function of x, so you can see z is a function of some intermediate variable y, and y is a function of x. Then we know that z must be a function of x as well. Right? And then how do we compute partial derivative of z with respect to x? According to the chain rule, it is simply you first take the partial derivative of z with respect to y, right? And then you're going to multiply partial derivative y with respect to x, right? That's the chain rule. Any question? It's just the formula, right? So now I want to give some like a graphical representation to show how this is computed. So we're going to use nodes to represent different variables. Right? There might be some dependency between them. We have three variables, right? Z, y, and x. Right? So we know z is a function of y. Then we draw an edge connecting y and z. Right? Y points to z. And we know y is a function of x. Then we draw a connection we draw a link between x and y. Right? So then from the graph structure, we can infer the dependency between z and x. Why? Because from x to z, there is a path, right? That actually shows the functional dependency. And then on each edge, we can attach a partial derivative, which is the partial derivative of the parent node over the partial derivative of the from node, the to node and from. So in this edge, right, which indicates the dependency from y to z, we can place an intermediate result, which is partial z or partial y. And similarly, on this edge, which indicates the dependency between y and x, we put partial y or partial x. So now, to compute partial z or partial x, from a graph point of view, we can simply look at the path from x to z. Then multiply all the intermediate partial derivatives along the path. Then we get the final result, partial z or partial x. Right? So now, our partial z or partial x is partial, the path. There is only one path from x to z, right? So you're going to multiply all the partial derivatives along this path, which is partial y or partial x, times partial z or partial y. That's it. This sounds like too straightforward. It's kind of like naive, right? But now let's make it a little bit complex. So suppose z is a function of two variables, y1 and y2. Right? And both y1 and y2 are functions of x. And now we still want to compute partial z or partial x. Right? And according to definition, you can recite the formula of chain rule, you can write down your own result. Right? But now let us attach the computation to the graph, to a dependency graph. So we got z1, y2, and x, right? So we got four variables. First, z depends on y1, z depends on y2, right? So there are two edges connecting to z, right? And then y1 is a function of x, so there's an edge connects to y1 from x, right? And y2 is a function of x as well, so there's a link from x to y2 as well. Again, on each edge, we're going to attach the partial derivative of the ending node over the partial derivative of the front node, right? So all here, partial z over partial y1, partial z over partial y2, partial y1 over partial x, partial y2 over partial x, right? So now, if we want to compute partial z over partial x, following the graph structure, we just need to enumerate all paths from x to z. And then for each path, we multiply the partial derivatives along that path. Then we add up the results over all the paths. That's how from the graph we can compute the partial derivative. Okay? So how many paths do we have connecting x to z? Two, right? One is left, one is right. So we need to add two results. Right? For the first result, we need to multiply the partial derivatives along the first path, right? Which is partial z over partial y1 times partial y1 over partial x, which is this left term, right? And for the second path, again, we multiply all the partial derivatives along the path, which is partial z over partial y2 multiply partial y2 over partial x is here, right? Now, you add them together. You got the final partial derivative of z with respect to x. Does it make sense? Okay. So now, in general, assume that your z is a function of n variables, y1, y2 to yn, right? And each intermediate variable is also a function x. If you want to compute partial z over partial x, you're going to go through each of these n paths, right? And for each path, you just multiply the partial derivatives along this path, which is partial z over partial yi times partial yi over partial x, right? Now you add up the results from every path. That's the general case. Why is a graphical representation so useful? Because when the dependency becomes large and complex, you will soon get lost if you just apply, recall the formulas of chain rule to do that. So it's always much easier and intuitive to use graph structures to state which terms should be added, which terms should be multiplied, and which terms should be collected. Does it make sense? Any questions so far? Okay, so now let us apply the chain rule to calculate the loss function with respect to the weights on our sample neural network, right? So suppose we want to calculate the partial derivative of our loss. Here we use square loss with respect to this weight W010, right? And some weight which on the edge connecting the neurons between the input layer and data layer, WIGH, right? Let us get some sense how this calculation is done, and then we'll proceed to the key idea of the backpropagation. So let us write partial L over partial W010, right? How to compute this? Let us just naively apply the chain rule, right? So first, our loss function is function of 1, right? Remember, y star is the ground truth, is a constant. So L depends on y. And the y depends on W0, right? here we list the rule to compute y. Remember, the output neuron is simple linear combination of the hidden neurons, right? We don't perform nonlinear activation function. So now to apply the chain rule, we're going to first compute partial L over partial y, right? And then partial y over partial W01O, right? What is partial L over partial y?
Y minus y star.
Yeah, exactly, right? Just take the derivative over this square term, right? It's pretty straightforward, right? And then, what is partial y over partial W01O? 010 is 1, right? Remember, it connects to Z0, but Z0 is biospacious constant, it's number 1, right? So, this looks quite easy, right? We immediately get partial L over partial W01O, right? And now, we just multiply these results right, together. Now, let us look at partial L over partial W11O, right? The weight on the edge in the middle, right? How to calculate that? Yeah, the same procedure, right? L depends on y depends on W11O, right? So you're gonna first calculate partial L over partial y, and then partial y over partial W11O, right? But here, it worth attention, right? This one has already been computed. So if you can smartly catch them, and then you don't need to recalculate, right? So actually, back propagation, the key idea is to tell you how to smartly catch all the intermediate results so that you don't need to calculate everything from scratch. Okay? And then what is partial y over partial W11O?
Z1.
Here, right? D1, right? Remember, y is a linear combination of the hidden neurons, right? So it's D1. So now you just multiply them together. You get the second partial derivative, right? But let me emphasize again, right? Since we have already computed the first partial derivative, right? We need to catch it to speed up. Right? So we can follow the same procedure to calculate partial L or partial W21, right? So I'm not gonna repeat. So now let us look at a little bit more challenging case. How to compute partial L over partial W22H. Okay. How to do that?
Follow the path.
Yeah, follow the class. And can you be more, a little bit more in detail?
First is the derivative over W of 210, and then W 22H.
Oh, you mean the derivative over W210? That's a little bit problematic because W210 actually does not depend on W22H. If you look at how we compute those neurons, which nodes depend on W2H? Yeah, exactly, right? So that's something I want to make you attract your attention. That is, usually those weights on different edges are not dependent on each other. Why? Because they're just a linear combination of the previous neurons. Right? It does not give you the prediction of those weights. Those weights are kind of independent. I mean, the independent does not mean like statistically. It just means in the computation sense. Okay, so now let us try to apply the chain rule, right? We just stick to the original definition, and then we'll try to look for some trick to save the computation, right? So if we want to compute partial L over partial W22H, again, apply the chain rule, which is partial L or partial Y, because L is directly dependent on Y, right? And then partial Y over partial W to the H. Okay. And then from the narrow structure, we can see that Y is immediately dependent on Z0, Z1, and Z2, right? So we can recursively apply a chain rule, right? So we're gonna rewrite partial Y over partial W to the H by partial Y over partial Z0 times partial Z0 over partial W to the H plus partial Y over partial Z1 times partial Z1 over partial W to the H, then partial Y over partial Z2 over partial Z2 over partial W to the H, right? This is just to apply the chain rule. Now the question is, what is partial Z0 over partial W to the H and partial Z1 over partial W to the H? And now? Zero. Over 0. Different opinions? Are they 0? Yeah, it is 0. Like, if you don't believe it, you can calculate. You can take a look at how you calculate Z0. Z0 is 1, right? It's constant to W to the H. And the Z1 is computed from a linear combination of the inputs by the different set of weights. Remember, the weight W to the H is on this specific edge, right? It does not connect to Z1 at all. So Z1 has nothing to do with W to the H. And you can now check the calculation of Z1 here, right? So it doesn't contain any term related to W to the H, right? So that means the first two partial derivatives is simply 0, right? You can just take them out. And then the remaining is just simply the product of three terms, right? Partial L over partial Y, and partial Y over partial Z2, and then partial Z2 over partial W to the H. Right? So now you can see things becomes a little bit complex because we have a large network. Right? The dependency between weights and the dependency among rows are kind of complicated. Right? So in this case, to determine which partial derivative should be cancelled, which partial derivative should be used or calculated, you need to look at the graph structure. Right? So you can see that, okay, W to the H, it only connects to Z2. And between Z2, Z0, and Z1, there is no path. Right? When we talk about path, I mean directed path. Right? So there is no path. That actually indicates there is no computational dependencies. Then that means the partial derivative of those irrelevant neurons with respect to W to the H is simply 0. Okay, let us stop here today. And on next Thursday, we're going to give a more general definition about how to find out the related or dependent neurons for any particular edge. This is edge weight. This is important.